The wildest thing about the wandering Earth is not the engines. It is the deadline. The story needs the sun to turn dangerous almost overnight, so Earth has to flee now. Real stars do not work like that. The sun changes on nuclear timescales set by fusion rates and long-lived balances inside the star. Even when the sun eventually swells toward a red giant phase, that transition is not a sudden surprise. It is a slow, modelable evolution that plays out over vast stretches of time. So the movie is right about the direction of the threat, but disastrously wrong about the tempo. That timing matters because urgency forces a single, extreme solution. If humanity had hundreds of millions to billions of years, moving Earth would be only one option. And it would probably not be the first choice. You could imagine orbital habitats, moving populations, major solar system engineering, even changing the sun itself through star lifting. Turning Earth into a ship is dramatic, but not efficient when time is abundant. Now suppose you ignore the calendar problem and try to move Earth anyway. The numbers become their own kind of science fiction. Earth's mass is about 6 times 10 to the 24 kilograms. To change Earth's speed by only 10 kilometers per second, a scale relevant to planetary orbits, you need an impulse around 6 times 10 to the 28 Newton seconds. Spread that over a century, and you still need a continuous thrust of roughly 2 times 10 to the 19 newtons. At that point, the engine bell shape is not the main issue. The planet itself becomes the engineering problem. You have to push on the crust without crushing it. You have to throw reaction mass away because propulsion means momentum exchange, not just energy. You have to run an energy source for centuries to millennia, and you have to dump waste heat constantly without cooking the biosphere and the underground cities. Fusion torch engines are a real class of ideas in the literature, at least as concepts. The catch is that high-power systems create brutal heat management problems. In the film, those problems scale up to the whole planet. If your engines are strong enough to shift Earth meaningfully, they are also strong enough to cause extreme heating, violent plumes, erosion, seismic stresses, and atmospheric disruption. The movie's most famous set piece, the near miss at Jupiter, is where several real concepts collide. Gravity assists are real. Spacecraft steal a little orbital energy from a planet by passing through its gravitational field on the right trajectory. But gravity assists work best when the traveler is small, nimble, and can be corrected precisely. Earth is none of those. For the movie's drama, Earth passes close enough to Jupiter that the atmosphere starts getting pulled away and global quakes spread. If you are close enough for that kind of stripping, you are in a regime where tides become catastrophic. That is where ideas like the Roche limit start to matter, the distance inside which tidal forces can disrupt a body that is held together mainly by gravity. Earth is dense and rocky, so it is tougher than an icy rubble pile moon. Even so, a sufficiently close pass would mean huge tidal stresses, ocean displacement, crustal deformation, and likely the loss of a lot of atmosphere. There is also a control problem the film quietly waves away. The story treats Earth's path like a threadable needle, as if you can steer a planet the way you steer a spacecraft. But a planet has no simple attitude control system. It has a rotating, lumpy mass distribution, oceans that slosh, an atmosphere that pushes back, and internal structure that flexes. Low-thrust navigation is hard even for probes. For Earth, every small correction costs a colossal impulse, and every impulse has consequences everywhere. Then comes the rescue idea. igniting Jupiter using oxygen from Earth. It sounds metal and it looks great, but it is not workable as presented. Jupiter is mostly hydrogen and helium, yes, but turning that into a sustained burn is not like lighting a campfire. You would need the right mix, the right conditions, and a mechanism to keep the reaction going. A gas giant is not an engine cylinder you can pressurize and spark on command. Where the film earns real credit is in the survival picture once Earth leaves normal sunlight. Without enough solar energy, photosynthesis collapses. Surface ecosystems fail. Oceans freeze from the top down. Atmospheric circulation and chemistry shift in harsh ways.